Everyone has started talking about heat waves. You have seen the headlines. Record temperatures. A heat dome over the southwest. Europe baking in May. And most of that coverage is telling you the truth as far as it goes. But here is what almost none of it tells you. The heat waves are not the story. They are the symptom of something that has been building for months. A structural breakdown in the atmosphere that has already rewritten the record books. Not once, not in one place, but simultaneously on both sides of the planet, in a pattern that the world's most sophisticated forecasting systems have never seen at this intensity before. What is actually happening, what is physically underway right now, is not visible from your window or readable in a weather forecast. It is happening in a layer of ocean hundreds of meters beneath a surface that looks, to the casual eye, almost normal. A pulse of heat the size of a continent is moving east through the deep Pacific at a pace of roughly a meter per second. And the last two times a pulse like this reached the surface, the world experienced the strongest disruptions to global weather in the modern record. That pulse has already started rising. By the time it fully surfaces, and NOAA now puts the probability of that happening at 96%, the event will be well past the point of prevention and most of the way to its peak. The atmosphere is not warming towards something, it is already inside it. And the surface numbers you have been reading, as alarming as they are a lagging indicator of a system that has already moved on to the next chapter. Stay with me, and I will show you the whole machine. How a broken jet stream over your head connects to a hidden thermal engine beneath the Pacific, and what that combination is likely to do to the weather you will actually live through over the next 18 months. If this is the kind of story you come here for, subscribe and turn on notifications, because we will be tracking every step of this as it develops. Drop a comment and tell me where you are watching from and whether the seasons where you live have started to feel wrong. Because, if they have, you are not imagining it. Let's break this down. Something unusual is happening to the United States this week, and the unusual part is not the heat itself, it is the geometry. Two separate large-scale heat domes are simultaneously active on opposite ends of the country. In the desert southwest, Arizona, Nevada, California's interior, and stretching up into Colorado and Utah. A high-pressure ridge has been anchored in place, producing temperatures that are running 20 to 30 degrees above what is normal for this time of year. Phoenix, a city that knows heat the way Boston knows cold, has been logging temperatures that rival its summer peak. In the interior southwest, the thermometer has been reading above 110 degrees Fahrenheit for multiple consecutive days. Not in July. Now, in a calendar window that, historically, still belongs to what most Americans would recognize as spring. On the other end of the continent, a separate but mechanically related high-pressure system, what meteorologists call a Bermuda High, has been anchored off the eastern seaboard, pumping heat into the northeast and mid-Atlantic, with the persistence of a system that should not be this strong this early at this latitude. The National Weather Service issued a heat advisory covering New York City and New Jersey on May 19, 2026. As temperatures pushed into the low 90s across a region where the buildings are old, the air conditioning is uneven, and the infrastructure was not designed for this calendar date to look like the second week of August. Pause on that. A heat advisory for New York City. In May, the School District of Philadelphia, on May 20th, transitioned 57 schools to fully virtual learning. Not because of a storm, not because of a winter emergency, because the aging school buildings could not safely manage the indoor temperatures produced by a late May heatwave that the district's infrastructure was simply never built to handle. In Lancaster County, a localized power outage compounded the thermal stress, forcing an emergency early dismissal. Dozens of school districts across New Jersey triggered emergency protocols. These are not the logistics of a summer heat event managed by a prepared system. These are the logistics of a May heat event that found a system operating well outside its design parameters. The power grid story is the operational number that does not make it into the evening news, but it is the number that tells you how consequential this event actually is. On Monday, May 18, 2026, PJM Interconnection, the grid operator managing electricity for 67 million Americans across 13 states and the District of Columbia, declared an Energy Emergency Alert Level 1. That is not a precautionary designation. That is the declaration a grid operator makes when it cannot meet its own reserve requirements. The specific numbers in the PJM Situation Report were these. 40,400 megawatts of planned generation capacity had been taken offline for scheduled maintenance. Nobody anticipated a heat demand event of this scale in the middle of May, and the maintenance windows were opened on that assumption. When the heat arrived anyway, PJM was projecting less than 5,800 megawatts of reserves against a projected peak demand of approximately 135,000 megawatts. The operator recalled every generator it could. It revoked scheduled maintenance windows. It issued a max generation and load management alert. It asked the federal government for permission to disconnect data centers from the grid to protect residential load. A grid emergency. In May, driven by heat that was not supposed to exist on this calendar date at this intensity. These are the operational facts of the current moment. They are verifiable and verified. But they are also, individually, incomplete as a story. The school closures and the grid emergency and the Phoenix temperature readings are the symptoms. They are what the atmosphere is doing to the systems humans have built. The cause, the physics that produced this configuration, the atmospheric setup that put two separate high-pressure ridges on opposite ends of the same continent at the same time, requires a different kind of examination. And the significance of that cause, the reason this particular moment is not just a bad heat wave but a signal of something larger, requires going somewhere most of the coverage of this event has not gone. The dual heat dome configuration is the first thing worth understanding precisely because it is rare. A single heat dome, a single anchored high-pressure ridge, producing a regional heat event, is not unusual. They happen every year in the American Southwest in summer, and in recent years they have been arriving earlier and running hotter. But two simultaneous, geographically separated high-pressure systems, one anchored over the interior west and one anchored off the eastern seaboard, operating at the same time with enough combined coverage to place anomalous heat on both coasts simultaneously, that configuration requires a specific atmospheric setup. And the atmospheric setup that produces it has a name, a mechanism, and a context that makes the current event significant beyond its immediate human impacts. The jet stream is a river of fast-moving air circulating around the planet at altitudes between roughly 30,000 and 40,000 feet. It is, in the most practical sense, the infrastructure of North American weather. Under normal conditions in late spring, the jet stream moves with some regularity from west to east across the continent, carrying weather systems with it and preventing any single high-pressure feature from parking itself over a region for more than a few days. When the jet stream is strong and relatively straight, the technical term is amplified zonal flow. It is like a fast-moving current in a river. Obstacles don't accumulate. Weather moves. What is happening right now is the opposite of that. The jet stream is currently configured in an exaggerated, highly amplified wave pattern. The technical term for this is a Rossby wave, a large-scale undulation in the atmospheric flow at upper levels. When a Rossby wave amplifies beyond a certain threshold, the troughs, the southward dips in the wave, and the ridges, the northward bulges become deep enough and slow enough that weather systems can stall. A high-pressure ridge, instead of moving east and dissipating within days, becomes locked in place. Beneath it, air sinks, compresses, and heats. The ground bakes dry. The dry ground radiates heat back upward. No clouds form. No rain falls. The surface heating feeds the ridge traps more heat, and the event sustains itself in a feedback loop that, once established, is extremely difficult to break. The configuration that has produced the current dual heat dome involves a deep trough positioned over the central United States. A northward displaced cold pool that is simultaneously separating the two high-pressure systems and mechanically coupling them, the way two adjacent gears turn in opposite directions while sharing the same mechanical energy. The Southwest Ridge and the Bermuda High are not two unrelated events that happen to be occurring simultaneously. They are two expressions of the same wave structure, one atmospheric pattern producing two heat events on opposite coasts. That is the geometry. That is the mechanism. And it is important to hold that mechanism clearly in mind for what comes next, because it is not only producing heat. The same wave that is sitting heat domes on the southwest and the east coast is simultaneously producing fire weather conditions across portions of the northern plains. It is simultaneously fueling severe storm development in the central United States, where the atmospheric instability on the eastern flank of the trough is generating the kind of thermodynamic conditions that breed supercell thunderstorms and tornado outbreaks. One wave, simultaneously producing heat, fire weather, and violent storms across the full breadth of the continent. Not as three separate weather stories, as one. This is the day the United States is currently having. Not a bad summer heat wave. A multi-hazard atmospheric event driven by a single wave configuration operating in May, in a climate system that has just finished its warmest 12-month period in 132 years of data. The heat is the part you can feel. The wave is the part you need to understand. And the thing building in the Pacific is the part that explains why this is not the end of the story. It is the beginning. There is a phrase that entered the popular vocabulary of extreme weather sometime around 2021 and has since been used with such frequency in headlines, in social media posts, in the opening lines of television forecasts, that it has largely lost its precision. The phrase is heat dome. It has become shorthand for "it is very hot," which is a significant reduction of what it actually describes. Understanding what a heat dome actually is, not as a metaphor, not as a shorthand, but as a physical process unfolding in 3 dimensions across thousands of feet of atmosphere, is essential to understanding why the current event is structured the way it is, why it is so persistent, and why events like it are so difficult to break once they begin. Start with the jet stream, because the jet stream is where this story begins. The jet stream is a narrow, fast-moving corridor of wind that circulates around the planet at altitudes of roughly 30,000 to 40,000 feet, the same altitudes where commercial aircraft cruise, which is not a coincidence. Pilots have been riding and fighting the jet stream for as long as powered flight has existed. The jet stream is driven by the temperature contrast between the cold polar air to the north and the warmer tropical air to the south. The greater that contrast, the tighter and faster the jet stream flows. Think of it as a pressure gradient converted to motion. The bigger the temperature difference between the two air masses, the harder the atmosphere pushes the jet stream along its path. Under normal conditions in late spring, the jet stream tracks roughly west to east across North America at a latitude somewhere between the Canadian border and the Great Lakes, with moderate undulations. Weather systems form on the southern edge of the jet stream, and the jet's eastward motion carries them progressively across the continent. A high-pressure system that forms over the desert southwest in May will, under normal conditions, drift east and weaken within a week, replaced by the next system in the atmospheric queue. The weather moves. That is the baseline state. What disrupts that baseline is a process that operates on the scale of the entire hemisphere. As the temperature contrast between the Arctic and the mid-latitudes has diminished, a well-documented consequence of the fact that the Arctic is warming roughly 2 to 4 times faster than the global average, the pressure gradient that drives the jet stream has weakened. A weaker jet stream is a more meandering jet stream. Instead of flowing in a tight, relatively straight band, it develops large, exaggerated waves. These are Rossby waves, named for the Swedish-American meteorologist Carl Gustaf Rossby, who described the dynamics of large-scale atmospheric undulation in the 1930s. Rossby waves are a normal feature of the mid-latitude atmosphere. What is not normal, or more precisely what is becoming more common than the historical record suggested it should be, is Rossby waves amplifying to the point where they stall. When a Rossby wave amplifies beyond a certain threshold, the troughs, the southward dips in the jet stream, and the ridges, the northward bulges, become so deep and so slow that they effectively stop moving. The atmosphere enters a state meteorologists call blocking. One specific blocking configuration, the one most directly relevant to the current situation, is the omega block. The name comes from the shape the jet stream traces when it encounters this pattern, a high-pressure system flanked on both sides by deep troughs of low pressure, with the jet stream curving up and over the high and diving back down on either side, tracing the shape of the Greek letter omega, omega. It looks, on a weather map, like a mountain of air with 2 valleys on either side. Inside the omega block's central ridge, something specific and relentless happens to the air. High-pressure systems are defined by one fundamental dynamic: air sinks. This is the opposite of what happens in a low-pressure system, where air rises. In the descending air column of a high-pressure ridge, something called adiabatic warming occurs. This is not a small effect. It is the central physical engine of the heat dome, and it operates according to a fixed thermodynamic constant that does not bend for the weather or the calendar. The dry adiabatic lapse rate is 5.4 degrees Fahrenheit per 1,000 feet of altitude change. This number comes from basic thermodynamics. When a parcel of dry air descends, the increasing atmospheric pressure surrounding it does work on the parcel, compressing it, and that compression converts to internal energy. The air heats, not because the sun is shining on it, not because it was already warm. It heats because of the physics of compression. At a rate of 5.4 degrees per 1,000 feet, air descending from 10,000 feet arrives at the surface already 54 degrees hotter than it was when it started its descent. This is the engine that is running inside every heat dome every time, regardless of what season it is or what the baseline temperature happens to be. Now add the secondary effects, because adiabatic compression is only the beginning. Descending air in a high-pressure system suppresses cloud formation. The mechanism is direct. Clouds form when rising air cools to its dew point and water vapor condenses. In a region of sinking air, that condensation cannot happen. The inversion. Warm air sitting atop cooler surface air acts as a lid, preventing the lower atmosphere from convecting upward the way it normally would. No convection means no clouds. No clouds means the full intensity of solar radiation reaches the ground surface unfiltered and uninterrupted, for days or weeks at a stretch. The sun is doing maximum work on a surface with no shade and no cooling from cloud cover. And here is where the feedback loop begins, because this is the point at which the heat dome stops being a passive physical phenomenon and starts being an active self-reinforcing system. The ground absorbs that concentrated solar radiation and heats. As it heats, it dries out. And here is the critical transition. A wet or vegetated surface handles incoming solar radiation by using much of it to evaporate water, a process called evapotranspiration. The energy goes into phase change, into converting liquid water to water vapor, and the surface temperature stays relatively controlled. A dry surface cannot do this. It has no water to evaporate, so instead of going into phase change, essentially all of that incoming solar energy goes directly into sensible heat, into raising the temperature of the surface itself. The dry ground gets hotter than wet ground would under the same sun, and it radiates that heat back upward into the lower atmosphere. Research published in the Proceedings of the National Academy of Sciences examining the 2021 Pacific Northwest heat dome found that this soil moisture feedback was not incidental to that event. It was a primary amplifier. An extended period of atmospheric blocking in the weeks before the peak of the heat event had already dried the soil across the region. When the Omega block achieved maximum amplitude in late June 2021, it found a landscape that had been preconditioned for maximum surface heating. The two processes, atmospheric blocking above and soil moisture deficit below, interacted non-linearly. Each amplified the other. The result was temperatures that broke records not by a degree or two, but by margins that meteorologists and climatologists described as statistically implausible for the current climate. Portland, Oregon, hit 116 degrees Fahrenheit, shattering its all-time record by 9 degrees. The small town of Lytton, British Columbia, reached 121.3 degrees, Canada's all-time record, broken 3 days in a row, before the town burned to the ground in a wildfire the following day. A study in the journal Nature Communications described the temperatures in the Pacific Northwest during that event as the hottest the region had experienced in a millennium. That is what an Omega block, combined with preconditioned dry soils and the full thermodynamic machinery of adiabatic compression, can produce. That is the system that is currently running on both coasts of the United States simultaneously in late May 2026 in a soil moisture environment that, after the driest January through March in recorded U.S. history, the driest on record since 1910, is not starting from a position of moisture surplus. Now add one more layer to this picture, because it is the layer most consequential for how long the current configuration persists. The subsidence inversion created by a heat dome is self-stabilizing in a specific and important way. As the ground heats and radiates energy back upward, it warms the lower layer of the atmosphere. But the descending air aloft is also warm. Warm from compression. What you get is a situation where the atmosphere is warm at the surface, warm above the surface, and the temperature difference that would normally drive vertical mixing, cooler air above, warmer air below, leading to convective overturning, has been largely erased. The atmosphere becomes stable against convection. Clouds cannot form not just because the air is sinking, but because the temperature structure of the entire air column actively resists the vertical motion that would produce them. Even isolated thunderstorm development, which is one of the mechanisms by which heat domes eventually break down, becomes suppressed. The dome insulates itself. There is an additional dimension to the current configuration that distinguishes it from a single, isolated heat dome. The driest January to March period on record across the contiguous United States has left the country's soil moisture in a state that amplifies the surface heating feedback across an enormous geographic footprint. The NOAA data is explicit on this point. The January through March 2026 period was the driest on record for the contiguous US, less than 70% of average precipitation, breaking the previous record set in 1910. Drought had expanded to nearly 60% of the contiguous United States, the largest drought footprint since November 2022. California, which recorded both its warmest and driest March on record, entered the heat dome season with essentially no moisture buffer. Arizona, Nevada, Utah, and Colorado were in the same state. What this means practically is that the surface heating feedback, the mechanism by which dry ground radiates more heat than wet ground, amplifying the dome, is operating across a broader area and with more intensity than it would in a moisture-normal year. The preconditioning that research identified as a key amplifier of the 2021 Pacific Northwest event is already present at the continental scale at the beginning of the 2026 heat season. The heat dome is not a metaphor for summer. It is a specific atmospheric machine with specific inputs, specific feedback mechanisms, and a specific set of conditions that make it more or less powerful. Right now, across the contiguous United States, most of those conditions are aligned for maximum output. The omega block is in place. The soil is dry. The inversion is holding. The jet stream is in a configuration that is not breaking the pattern. And beneath the Pacific Ocean, something is adding heat to the system that was not part of the equation in 2021. That is the part we have not gotten to yet. On April 8, 2026, NOAA's National Centers for Environmental Information released its monthly climate summary for March. The document is a federal report. It is written in the measured, calibrated language of government scientists who are professionally disinclined toward dramatics. And what it describes is, by any historical standard, extraordinary. March 2026 was the warmest March in 132 years of contiguous U.S. temperature records. The average temperature across the lower 48 states was 50.85 degrees Fahrenheit. That is 9.35 degrees above the 20th century average for March. To understand why that number is significant, consider this. March 2012 previously held the record for the most anomalous month in the modern record, at 8.9 degrees above average. March 2026 didn't just break that record. It broke every prior monthly anomaly record across all 12 months of the calendar. Not the hottest March ever. The most abnormally hot month ever recorded in the United States, measured against baseline in 132 years of data, through the Dust Bowl, through the climate disruptions of the 20th century, through every summer on record, no month in any season had ever exceeded 9 degrees above baseline. March 2026 was the first. The scale of individual records embedded within that monthly average is worth examining precisely, because this is where the abstract becomes concrete. Weather observation stations across the country broke 10,763 daily record highs in March alone. Not monthly records. Daily records, the highest temperature ever recorded on a specific calendar date at a specific station, going back in many cases 50 to 100 years. 10,763 of those fell in a single month. Stations also broke 1,924 monthly high maximum temperature records and tied 682 more. In 1,432 counties, more than half the continental United States, covering 1/3 of the total population, residents experienced their single warmest March day on record. Arizona ran 14 degrees above its 20th century March average. New Mexico ran 12 degrees above. Both states set all-time March records. 10 states in total recorded their warmest March in history. The average daytime high temperature for March 2026 ran not just above the 20th century March average, but nearly a full degree above the long-term average daytime high for April. The month of March, in terms of daily temperatures, performed as if it were April. In several locations across the Southwest, Los Angeles International Airport, San Francisco International Airport, March 2026 temperatures exceeded those stations' current records for the warmest April they had ever recorded. March was hotter than those stations' record warm April. The calendar had been reordered. The precipitation story was equally stark. The January through March 2026 period was the driest first 3 months of any year on record for the contiguous U.S. Less than 70% of average precipitation, breaking the previous record set in 1910. California received less than a quarter inch of precipitation statewide, record dry. Nearly 60% of the contiguous U.S. entered April under drought conditions, the largest drought footprint since November 2022. Now step back from the individual month and look at the 12-month window that March closed. April 2025 through March 2026 now stands as the warmest 12-month period ever recorded for the contiguous United States in data going back to 1895. Not this spring, not this winter, the trailing 12 months ending March 31st, 2026, were the hottest consecutive 12 months in 132 years of American climate records. And every 2-month, 3-month, 18-month and 24-month window going backward from that date is also the warmest in the record, according to Yale Climate Connections analysis of NOAA's Climate at a Glance tool. The meteorologist at Climate Central, Shel Winkley, described March 2026 as unprecedented in a statement worth noting for its precision. Not because of any single record, but because of the sheer volume of all-time record. Records at the all-time tier, not merely seasonal, were being set across the country at a rate that statistically should not be possible within a single calendar month. According to Weather Channel analysis by meteorologist Brian Brettschneider, when considering all major weather reporting stations with at least 100 years of daily data, more of those stations set monthly warm records in March 2026 than in any other month in the historical record, including the heart of the Dust Bowl in July 1936. 6 of the 10 most anomalously hot months in U.S. history have now occurred in the last 10 years. There is a framing choice to make when confronting a number like that, and it is worth making it explicitly. One framing is that these are the inevitable consequences of a warming trend that has been building for decades, and that a month like March 2026 is simply the most recent peak in a sequence that will continue to produce new peaks. That framing is consistent with the data. The other framing, and this is the one that has atmospheric scientists genuinely focused, is that March 2026 did not happen in isolation. It happened at the end of the warmest 12-month stretch in American history, 2 months before a potential super El Niño begins to fully develop. It happened as prologue, not as climax. The warmest month in 132 years of records occurred before the event that is building in the Pacific has even arrived. That is the sentence that should hold your attention. Not because it guarantees what comes next, but because it establishes the baseline from which whatever comes next will depart. There is a specific sentence written by researcher Deirdre Desjardins in a March 2026 analysis published through California Water Research that deserves to be read carefully. It is this: the March 2026 heat dome was not a bolt from the blue. It was the most extreme pulse in a winter-long pattern that locked the western United States into warmth and the east into cold for months. Those 10,763 daily records, that 9.4-degree anomaly, they did not emerge from nowhere. They were the peak of something that had been building since December. Understanding what that something was is what separates a weather story from a climate story. Winter 2025. 26 was the warmest on record across the majority of the American West. Phoenix, Denver, and Las Vegas ran above normal through December. 9 states broke all-time winter temperature records by February. Salt Lake City recorded its least snowy winter on record. The snowpack across the upper Colorado Basin was already critically below average before March arrived. The soil was dry, the cooling buffer that normal winter snowpack provides, insulating the ground, moderating spring temperatures, releasing moisture slowly into the soil as it melts, had been largely spent before the heat dome even formed. When the ridge arrived in March, it found a landscape preconditioned to amplify it. The ridge itself had an unusual source. Climate scientist Daniel Swain and researcher Desjardins both identified the mechanism independently. Back-to-back intense Kona-low subtropical cyclones struck Hawaii in early March, dumping over 2 trillion gallons of water on the islands and generating a powerful atmospheric river riding the jet stream toward the Pacific Northwest. As that moisture-laden air ascended rapidly in the warm conveyor belt of the cyclone, water vapor condensed and released enormous quantities of latent heat, the energy stored in water vapor that gets liberated when it changes phase to liquid. That released heat reorganized the potential vorticity structure of the upper atmosphere above and downstream, producing a powerful ridge of low PV air that amplified across western North America. The ridge over the southwest was, in part, built by a rainstorm over Hawaii 2,500 miles away. Desjardins' second analysis went deeper into the structural question. Why does the western ridge keep forming? Her answer pointed to something more consequential than a single event's mechanics. The warm west, cool east pattern that dominated winter 2025-26 is not random. It has become a recurring feature of North American winters over the past decade. Research by Teng and Brandstater established that this pattern reflects a specific wave number 5 configuration of the polar vortex, 5 alternating ridges and troughs circling the northern hemisphere. And that tropical diabatic heating from the western Pacific warm pool can double the probability of extreme western ridging by projecting wave energy onto the atmospheric waveguide at precisely the right wavelength. The 500 millibar height field during March 2026 showed exactly this 5-lobed structure, with the western North American ridge grotesquely amplified relative to the others. The warmer, moister atmosphere that climate change is producing does not simply raise the background temperature, it changes the dynamics. In a warmer atmosphere, more water vapor is available for the latent heat release that builds ridges. More latent heat means stronger ridges. Stronger ridges mean more extreme heat domes when they stall. Desjardins' conclusion was precise. The specific type of block that produces record-shattering heat domes is the type that gets stronger with more moisture. The World Weather Attribution Rapid Attribution Study, released within days of the March event, made this explicit. Terms: human-caused climate change added between 4.7 and 7.2 degrees Fahrenheit to the temperatures observed. The event was not merely made more likely by climate change, it was described as virtually impossible without it. This is the context the broadcast coverage of the current May heat event largely omits. What is being reported as a heat wave is actually the continuation of a pattern that has been running for 7 months. December established the ridge. January and February deepened the drought and depleted the snowpack. March produced the most anomalous month in 132 years of US records. April brought a brief reset. And now in May, the dual heat dome configuration is back, operating against a soil and snowpack baseline that never recovered from the winter that preceded it. The pattern has not been interrupted. It has been reloading. On Sunday, May 25, 2026, weather station Kew Gardens in West London recorded 32.3 degrees Celsius. That made it the UK's hottest May day in at least 79 years. The record did not hold for long. The following day, it reached 34.8 degrees Celsius at Kew, surpassing the previous all-time May record for Great Britain of 32.8 degrees Celsius, a record that had stood since 1922. The day after that, May 27th, the record broke again at 35.1 degrees Celsius. The UK's all-time May temperature record has now been broken on consecutive days, twice, within 72 hours. This is not a separate story from what is happening in the United States. It is the same story. While the American Southwest baked under 110-degree heat, and PJM declared grid emergencies in the eastern United States, a heat dome built from northwestern Africa pushed northward across the entire European continent. Spain and Portugal ran sustained temperatures in the upper 30s Celsius, approaching 40 degrees Celsius in isolated locations. France logged its hottest May day on record, with station records broken in over 300 locations in a single day. And the French Prime Minister called an emergency government meeting on heat preparedness. Italy imposed restrictions on outdoor labor. Germany ran 30 to 33 degrees Celsius. The temperatures across Western Europe this final week of May are running 12 to 16 degrees Celsius above the long-term climatological average for late May. That is not a rounding error. That is the difference between spring and midsummer, imposed on an entire continent simultaneously. The UK's Climate Change Committee released a report last week with a sentence that deserves to be held: the UK was built for a climate that no longer exists. That framing is not hyperbole. Only around 5% of British homes have air conditioning. The country's infrastructure, its buildings, its train tracks, its grid, was designed around a thermal envelope that the current atmosphere is no longer respecting. Network Rail imposed speed restrictions on rail lines across the country as track temperatures threatened structural integrity. Hospitals reported elevated heat-related presentations. 5 deaths tied directly to the heat have been confirmed across the UK alone. The structural reason Europe is so vulnerable to precisely this kind of event is worth stating clearly. The European Union's Copernicus Climate Change Service confirmed in its 2025 European State of the Climate Report that Europe is the fastest warming continent on Earth, having warmed at roughly twice the global average rate since the mid-1990s, approximately 0.53 degrees Celsius per decade. At the continental scale, Europe is now running approximately 2.4 degrees Celsius above pre-industrial levels, compared to the global average of roughly 1.4 degrees. The 1.5 degrees Celsius threshold the Paris Agreement was designed to prevent the world from crossing has already been crossed, structurally, across Europe as a whole. The mechanism is well understood. Europe sits downwind of an Arctic that is warming 2 to 4 times faster than the global average, which weakens the temperature contrast that drives the jet stream's vigor, which produces more frequent and more persistent atmospheric blocking. The same omega block and heat dome dynamics described in Part 2, now operating at the European scale. Meanwhile, Europe's soil moisture has been declining under successive dry seasons, preconditioning the feedback loop that amplifies surface heating when a blocking high parks over the continent. The EU's aerosol pollution reduction efforts, environmentally correct, have also removed a partial solar shield that previously masked some of the warming signal. Europe is experiencing the climate that was always going to arrive here. It is arriving on this particular week. The significance of the global simultaneity is not incidental. It is the point. The United States and Europe are not experiencing 2 separate heat events that happen to coincide. They are experiencing 2 regional expressions of the same Northern Hemisphere atmospheric circulation pattern. A pattern characterized by multiple amplified ridges and blocked jet streams operating at the same time across different longitudinal sectors of the hemisphere. The same wave number 5 configuration that researchers identified as the structural driver of the March 2026 US heat dome is, at the hemispheric scale, also capable of producing concurrent heat events on multiple continents. When those ridges amplify simultaneously across different sectors, one over Western North America, one over Europe, the result is not a coincidence. It is a coherent planetary scale atmospheric state. Climate scientists are watching the simultaneity closely, not because 2 concurrent heat events in late May prove a direct causal link. They don't, and it would be scientifically dishonest to claim otherwise, but because the frequency with which this kind of hemispheric synchronization is occurring has been increasing, and because the background warming that makes each individual event more extreme also makes the simultaneous occurrence of multiple extreme events more likely. When the baseline is already the hottest 12-month stretch in recorded history, the threshold for a record event has been lowered for the entire hemisphere at once. What is happening this week on 2 continents simultaneously is not a weather coincidence. It is a signal. And beneath both of these continents, the same Pacific Ocean is warming. There is a feature of the current atmospheric setup that the broadcast coverage of this heat event almost universally omits, and it is arguably the most operationally significant thing happening in American weather right now. The same wave configuration producing the dual heat domes, the same Rossby wave, the same coupled trough and ridge system described in Part 1, is simultaneously producing fire weather across the northern and central plains, and has been fueling tornado outbreaks across the central United States throughout May, not separately, simultaneously. One pattern, every category of hazard. This is the multi-hazard dimension of the current setup, and understanding it requires understanding the geometry of the omega block's edges. The heat is not happening everywhere within the high-pressure system. It is concentrated beneath the center, where the sinking air is most intense. But on the flanks, the zones where the central ridge gives way to the flanking troughs, The atmospheric instability is extreme. Warm, moisture-laden air from the Gulf of Mexico streams northward into the eastern edge of the trough. It meets the cold, dry air descending from the north. The temperature and moisture contrast between those two air masses is the fuel for severe thunderstorms. The more amplified the wave, the stronger the contrast. The stronger the contrast, the more violent the convection. The Storm Prediction Center issued an enhanced risk, level 4 out of 5, for northeastern Kansas on May 17th, with moderate risk extending from the western Great Lakes through central Texas. That same system produced over 300 severe weather reports in a single day, primarily across the Great Lakes, Midwest, and Central Plains. The tornado reports were concentrated in northeastern Kansas, southeastern Nebraska, and southwestern Iowa, with confirmed tornadoes near Blue Rapids and in Washington and Marshall counties in Kansas. An EF3 struck St. Liberty, Nebraska, and a tornado emergency was issued for the city of Hebron, Nebraska. The same storm system that spawned those tornadoes simultaneously fueled rapid wildfire growth across the southern high plains through high winds and critically dry conditions. That conjunction, tornadoes and wildfires, produced by the same system on the same day, is not coincidental. It is structural. The western flank of the heat dome, where hot, dry air meets gusty downslope winds, is textbook fire weather territory. NOAA's Wildland Fire Outlook for May flagged above normal fire potential across the southwest and northern plains, simultaneously with the severe storm risks on the system's eastern edge. In the same calendar week that Philadelphia closed 57 schools due to heat and PJM declared a grid emergency, the Storm Prediction Center was issuing fire weather watches for Idaho, Utah, western Colorado, and Wyoming, while tornado watches were in effect from Texas to Indiana. The National Weather Service Chicago office noted in late April that the Storm Prediction Center had outlooked at least part of the Chicago forecast area for severe weather on 15 separate days through April alone, an unusually high number, with an abnormal frequency of enhanced or higher risk designations. The lower Great Lakes corridor from eastern Iowa through southern Wisconsin and northern Illinois have been described as remarkably active for the season. The pattern has been producing severe weather at one edge and fire weather at the other for months, since December. The same ridge that locked the western U.S. into its record-breaking winter warmth and preconditioned the drought also set up the atmospheric contrast on its eastern flank that has driven the severe weather season. These are not separate stories running in parallel. They are a single atmospheric story being read from different positions on the map. This is the underreported dimension of the current crisis. The United States is not experiencing a heat event. It is experiencing a continental-scale multi-hazard event in which every category of operational extreme, heat, fire weather, severe convection, flash flooding on the storm system's periphery, is running simultaneously, driven by a single wave configuration against a soil moisture and snowpack baseline that has been preconditioned for maximum amplification since winter. That is what is happening above the surface. Below the surface of the Pacific Ocean, something else is happening. Something that will determine the context in which every one of these patterns operates for the next 18 months. Everything described so far, the dual heat domes, the grid emergency, the European records, the tornado outbreaks, the fire weather corridors, is happening at the surface. It is the atmosphere doing what an anomalously warm jet stream disrupted climate system does. It is consequential. It is verifiable. And by itself, if that were the entire story, it would constitute an extraordinary set of events deserving serious attention. It is not the entire story. Beneath the surface of the equatorial Pacific Ocean, at depths between roughly 50 and 250 meters, below where you can swim, below where most marine life is visible, in the dark thermocline layer that separates the warm upper ocean from the cold deep ocean, something has been building and moving for months. And what it is, what it portends, and why the world's most sophisticated forecasting systems are now tracking it with an intensity that has no precedent in the modern record, is the actual subject of this video. The object in question is called a Kelvin wave. Understanding what a Kelvin wave is requires first understanding the normal state of the tropical Pacific, because the Kelvin wave is a deviation from that state, a deviation of enormous scale and consequence. Under normal conditions, the trade winds blow steadily from east to west across the equatorial Pacific, roughly from the South American coast toward Indonesia and Australia. Those winds do something physically significant. They push the sun-warmed surface water westward. Over time, this creates an imbalance. The Western Pacific, near Indonesia and the Philippines, becomes a reservoir of warm surface water, a region oceanographers call the Western Pacific Warm Pool, where sea surface temperatures regularly exceed 29 to 30 degrees Celsius, the warmest open ocean water on Earth. Meanwhile, the Eastern Pacific, off the coast of South America and Peru, is kept relatively cool by the process called upwelling, cold, deep water rising to replace the warm water that the trade winds have pushed away. The thermocline is the boundary between these two water masses. In the Western Pacific, it sits deep, perhaps 150 to 200 meters below the surface. In the Eastern Pacific, trade winds drive upwelling that pulls it as shallow as 20 to 50 meters. The whole system is in dynamic tension. Warm water piled in the west, cold water near the surface in the east, maintained by the steady easterly push of the trade winds. Now what happens when those trade winds weaken? When the trade winds relax, either gradually over weeks or abruptly in what meteorologists call a westerly wind burst, a period of days when the winds reverse direction and blow from west to east across the equator. The warm water piled up in the west is no longer being held there. Gravity takes over. The warm water begins to slosh back eastward, like water in a bathtub tilted and then released. This is the Kelvin wave, a massive pulse of warm water propagating eastward along the equator, not at the surface where satellites can easily observe it, but below, deepening the thermocline as it moves, suppressing the cold upwelling, and carrying heat eastward across the entire width of the Pacific. NOAA climatologist Michel Leroux described the Kelvin wave to the Washington Post with a precision worth repeating. Unlike the waves you see at the beach, Kelvin waves do not curl over and then crash. They are more like waves in your bathtub, which slowly slosh around. The 2026 Kelvin wave was triggered by a series of unusually strong westerly wind bursts that began propagating across the equatorial Western Pacific in late 2025, as La Niña conditions were still nominally in place at the surface. Those wind bursts pushed the warm water east. Downwelling Kelvin waves propagated eastward from November 2025 onward, carrying the subsurface heat anomaly along the thermocline towards South America. By May 2026, the wave had expanded across the tropical Pacific and is now surfacing in the eastern basin, where it is suppressing the cold upwelling that normally keeps sea surface temperatures along the South American coast cool. The specific numbers attached to the current Kelvin wave are what moved the forecasting community from cautious attention to operational alarm. The subsurface temperature anomaly, the departure from average, within the wave's core is running at approximately plus 8 degrees Celsius at depths between 50 and 250 meters across the central equatorial Pacific, 8 degrees Celsius above average. For comparison, the 1997-98 El Niño, currently the second strongest on record, produced a Kelvin wave of extraordinary scale and intensity. The 2026 Kelvin wave, at this stage of its development, is running warmer than the 1997-98 event did at the equivalent stage, warmer than 1997 at the equivalent point in the development cycle. NOAA researcher Michel Leroux told the Washington Post, "The current Kelvin wave is impressive, and by some measures we look at, it is rivaling the one we saw in 1997. That sentence was written by a government scientist at the Climate Prediction Center. It is not the language of alarm for its own sake. It is the language of calibrated comparison to the most significant El Niño in the modern instrumental record. The event that rewired global weather patterns for 18 months, killed thousands of people through drought, flooding, and fire across multiple continents, and remains the benchmark against which every subsequent warm ENSO event is measured. The Kelvin wave is currently surfacing. The warm water is arriving at the sea surface in the eastern Pacific. El Niño is not a forecast anymore. It is a process already underway. The question the models are now attempting to answer, the question that has the forecasting community issuing probability statements with unusual precision and unusual public visibility, is not whether El Niño will happen. It is how strong it will get. That question does not yet have a definitive answer. But the numbers attached to the leading candidate answers are the most consequential set of meteorological numbers in circulation right now. And the place to start with those numbers is with what El Niño actually does to the global atmosphere, because the mechanism matters as much as the magnitude. The phrase El Niño has been in the news cycle long enough that most people carry a loose impression of what it means. Warm water in the Pacific, disrupted weather patterns, a wet winter in California. That impression is not wrong. It is, however, radically incomplete. And the incompleteness matters, because what a super El Niño actually does to the global atmosphere is not a louder version of a normal El Niño. It is a qualitative restructuring of the entire planetary circulation system. To understand the scale of what the 2026 forecasts are describing, you need to understand the mechanism precisely. Start with the Walker circulation. The Walker circulation is the large-scale east-west loop of air movement in the tropical atmosphere, named for British meteorologist Gilbert Walker, who described it in the 1920s while trying to predict Indian monsoon failures. Under normal conditions, what climate scientists call ENSO-neutral, the trade winds push warm surface water westward across the Pacific toward Indonesia and Australia. That warm water heats the overlying air, causing it to rise, form deep convective thunderstorms, and release enormous quantities of latent heat into the upper troposphere. The rising air then spreads outward at altitude, moves east, descends over the cool eastern Pacific near South America, and flows westward along the surface again to complete the loop. It is a conveyor belt of atmospheric energy running continuously across the width of the Pacific, and it is the single most important driver of year-to-year climate variability on Earth. When El Niño begins, when the Kelvin wave delivers its heat pulse to the eastern Pacific and sea surface temperatures rise, the Walker circulation breaks down. The warm water that was concentrated in the west now spans the entire equatorial Pacific. The convective heating that previously anchored over Indonesia and the Philippines shifts eastward, or weakens entirely. The atmospheric pressure seesaw that Walker first documented, low pressure over the western Pacific, high pressure over the eastern Pacific under normal conditions, flattens and then reverses. This is what meteorologists call the Southern Oscillation, the atmospheric pressure signature of the ocean temperature anomaly. The two components, the ocean temperature change and the atmospheric pressure shift, are coupled through a self-reinforcing mechanism named the Bjerknes feedback, after Norwegian-American meteorologist Jacob Bjerknes, who identified it in 1969. Weaker trade winds allow warm water to spread east, which further weakens the trade winds, which allows more warm water to spread east. The system accelerates. What the Bjerknes feedback produces when it runs to full amplitude is not just a local warm spot in the Pacific. It is a full rewiring of atmospheric circulation patterns across the entire planet through what atmospheric scientists call teleconnections, the long-range remote responses of weather systems to changes in tropical ocean temperatures. The mechanism is the jet stream. El Niño's anomalous tropical heating feeds energy into the upper troposphere that propagates poleward and eastward in Rossby waves, the same class of atmospheric wave discussed in Part 2, altering the position, strength, and trajectory of the mid-latitude jet stream. Move the jet stream and you move everything downstream of it. Storm tracks, precipitation patterns, drought zones, temperature regimes, the cascading effects are global and simultaneous. India's summer monsoon weakens or fails because the shift in the Walker circulation disrupts the pressure gradient that drives moisture from the Indian Ocean inland. In strong El Niño years, monsoon rainfall deficits across India have been measured at 14% below normal, a figure that in a country of 1.4 billion people dependent on monsoon rains for agriculture and freshwater supply is not an abstraction, but a food security event. Australia and Indonesia dry out dramatically as the convective rainfall that normally anchors over the western Pacific migrates eastward away from them. The 2015-16 El Niño produced catastrophic wildfires across Indonesia that generated regional smoke so dense it constituted a public health emergency across Southeast Asia. Peru and Ecuador flood. The Amazon basin dries. East Africa sometimes floods, while Southern Africa droughts simultaneously. The Panama Canal, entirely dependent on reservoir water levels, has experienced restricted ship passage during 3 separate El Niño events because freshwater levels fell below operational thresholds. In the United States, El Niño shifts the Pacific jet stream southward and eastward in winter, strengthening the southern storm track and delivering anomalously wet conditions from California through the Gulf Coast and the southeast. It suppresses Atlantic hurricane formation by increasing upper-level wind shear. It warms the northern tier of the country. As University at Albany professor Paul Roundy described it in a recent interview, normally wet places become dry and suffer fires. Normally dry places become wet. But it describes a normal to strong El Niño. What is being projected for 2026-27 is not in that category. The threshold being discussed? The plus 2 degrees Celsius sea surface temperature anomaly sustained in the Niño 3.4 region that defines a super El Niño is not a benchmark that has been crossed often. Only 3 events in the entire modern instrumental record have done it: 1982, 83, 1997, 98, and 2015, 16. The current models are projecting anomalies approaching or exceeding plus 3 degrees Celsius by late 2026. That is not the mechanism at higher amplitude. At that level, it is a different animal entirely. And the world in which it would arrive, already running hotter than any 12-month period in recorded history, has never hosted one before. On May 14, 2026, NOAA's Climate Prediction Center issued its official ENSO diagnostic discussion and simultaneously upgraded the United States' formal ENSO alert status to El Niño Watch. The summary statement in that document was precise and unambiguous. El Niño is likely to emerge soon, with an 82% probability in the May through July window and a 96% probability of persisting through the December 2026 through February 2027 peak period. Those are not speculative projections. They are consensus probability statements from a federal agency, drawing on observational data, model output, and human expert judgment. They are, by any historical standard, extremely confident numbers to be issuing in May. 2 weeks later, the IRI/Columbia University Plume Forecast, a separate modeling system that runs independently of NOAA's CPC, updated its probability to 98%. Not 82, not even 96. 98% probability that El Niño conditions will be present through at least early 2027. The ECMWF's May 2026 Long-Range Ensemble Model Update assigned 100% probability to a Super El Niño forming by November, not to El Niño. To Super El Niño, the specific threshold requiring sustained anomalies of plus 20 degrees Celsius or above in the Niño 3.4 monitoring region. 100%. In a probabilistic forecasting system that is by design calibrated to never reach 100% on any climate outcome, the ECMWF's May update crossed that threshold, and the rate at which it got there was itself the alarming data point. The ECMWF tracker stood at 22% in March, reached 80% in late April, and moved to 100% in the May update. That rate of increase, from 22% to 100% in approximately 8 weeks, is faster than the ramp recorded in the lead-up to either the 1997, 98, or 2015-16 super events. These 3 modeling systems, NOAA's Climate Forecast System, the ECMWF, and Australia's Bureau of Meteorology, now converge on a peak Niño 3.4 anomaly of approximately plus 3 degrees Celsius by November 2026. 3 independent systems from 3 different continents, using 3 different modeling frameworks with different initialization data and different physical parameterizations, producing essentially the same answer. 3 degrees Celsius above the long-term average in the central equatorial Pacific by November. That figure requires context. The 3 Super El Niño events in the modern record, 1982, 1997, 98, and 2015-16, peaked at roughly plus 2 degrees Celsius, plus 2, 8 degrees Celsius, and plus 2, 5 degrees Celsius respectively. A plus 3 degrees Celsius anomaly would exceed all 3. The 1997-98 event, which remains the standard reference for a devastating Super El Niño in the modern era, caused an estimated $45 billion in damage globally, produced catastrophic flooding in California and the Gulf Coast, triggered the worst drought in the Philippines in decades, contributed to Indonesian wildfires that blanketed Southeast Asia in smoke, and, with its associated global temperature pulse, helped make 1998 the warmest year on record at the time. The 2026 event is being projected to exceed 1997 to 98 in peak intensity. It would do so against a baseline global temperature that is already roughly 0.4 to 0.5 degrees Celsius warmer than the baseline from which 1997-98 developed. The El Niño heat pulse compounds the existing warming. It does not replace it. NOAA's own CPC has now adopted language that represents a significant shift in institutional communication. A super El Niño is described in current CPC materials as the single most likely outcome for late 2026. That is not the language of hedging. It is not the language of a model spread that keeps all outcomes equally plausible. It is the federal government's primary climate prediction agency stating in plain terms that of all the possible trajectories this event could take, the one most likely to verify is the one at the high end of the historical record. What the CPC and IRI are careful to note, and this intellectual honesty is worth stating explicitly, is that strong model consensus in May does not guarantee outcome. The spring predictability barrier still applies. The Bjerknes feedback, once established, is self-reinforcing, but it is not guaranteed to run to maximum amplitude. A 1 in 3 probability of crossing the superthreshold is in the other direction, a 2 in 3 probability of not crossing it. The models agree on a strong to very strong event. They assign roughly equal probability to a super El Niño and to a merely very strong one. That distinction matters. But what both outcomes share, what the entire probability distribution has in common, is an event of historically significant magnitude, arriving in a climate system already running hotter than any comparable period in the instrumental record. The question is not whether something consequential is coming. That question has been answered by the data. The question is how consequential. The word super in front of El Niño is not formal scientific terminology. It is a label that emerged from the popular and operational meteorological lexicon to describe something that the standard vocabulary of strong and very strong was insufficient to capture. But what it points to has a precise scientific definition. A super El Niño is an event in which the sea surface temperature anomaly in the Niño 3.4 monitoring region, a defined rectangle of the central equatorial Pacific, bounded by 5 degrees S to 5 degrees N latitude and 170 degrees W to 120 degrees W longitude, exceeds +2, 0 degrees Celsius above the long-term average and sustains that level for the required 3-month overlapping periods. That is the threshold. In the entire modern instrumental record, it has been crossed exactly 3 times. 198283, 199798, 201516. In roughly 75 years of reliable observational data, each of them constitutes its own chapter in the history of global climate disruption. The 198283 event arrived with almost no warning. Forecasting systems at the time were primitive compared to today's, and the event had already developed significantly before it was formally recognized. It produced what was at the time described as the largest synchronous global crop failure in the modern record. The cascade of droughts and floods it generated carried total global economic losses, eventually estimated at $4.1 trillion. It produced catastrophic drought across Australia, Indonesia, Southern Africa, and India. It produced catastrophic floods across Ecuador, Peru, and the Gulf Coast of the United States. It reshaped the scientific understanding of what NSO was capable of, and directly drove the investment in ocean monitoring systems, the Tau/Triton buoy array, that makes today's forecasting possible. The 1997-98 event was the benchmark for a generation of climate scientists. It peaked at roughly +2, 8 degrees Celsius in the Niño 3.4 region in November 1997, making it the strongest event in the modern record at that time. California flooded catastrophically. The Philippines experienced its worst drought in decades. Indonesian wildfires consumed millions of hectares of forest, producing regional smoke pollution so severe it was classified a public health emergency across Southeast Asia, and is estimated to have contributed to thousands of excess deaths. The disruption to the Peruvian anchovy fishery collapsed coastal fishing economies. Global economic losses in the 5 years following the event were estimated at $5.7 trillion. The 1998 calendar year, riding the temperature pulse of the event, became the warmest year on record at the time. The 2015 1/6 event matched 1997-98 roughly in peak intensity, approximately +2.5 degrees Celsius, and drove 2016 to become the warmest year on record, a record that stood until 2023. It produced severe coral bleaching across the Great Barrier Reef and global reef systems on a scale that alarmed marine biologists. It deepened drought across East Africa, contributed to crop failures across southern Africa, and shifted hurricane activity patterns in both the Pacific and Atlantic basins. Notably, and this is the honest counterexample that must always accompany this discussion, the 2015-16 event failed to deliver the anomalously wet winter to California that strong El Niños typically produce. The teleconnection held in some regions and failed in others. A super El Niño shifts the odds. It does not guarantee outcomes. Now, what does +3.0 degrees Celsius mean in relation to these three precedents? The straightforward answer is that +3.0 degrees Celsius would exceed the peak anomaly of all three events. But the more precise answer is that the relationship between ocean temperature anomaly and atmospheric response is not linear. At higher anomaly values, the atmospheric circulation response can amplify non-linearly, producing impacts that are not simply a proportional intensification of what +2.5 degrees Celsius produced. This is what UCL Emeritus Professor of Geophysical and Climate Hazards Bill Maguire meant when he told HuffPost UK that the 2 degrees Celsius threshold is critical, because once you cross it, the consequences multiply. The volume of heat being transferred from ocean to atmosphere at +3 degrees Celsius is sufficient, in the models, to physically displace the jet streams of both hemispheres into configurations they would not otherwise reach, producing simultaneous droughts, floods, wildfires, and monsoon disruptions across countries thousands of kilometers from the Pacific. There is one more element that makes the 2026 event categorically different from all three prior Super El Niños, and it is the one that climate scientist Nathan Lenson of NCAR stated directly. Climate change has made El Niño events of the past less informative for events today. The 1982-83 event developed in a global atmosphere approximately 0.3 degrees Celsius cooler than the pre-industrial baseline. The 1997-98 event developed in a global atmosphere roughly 0.6 degrees Celsius above pre-industrial. The 2015-16 event developed at approximately 1.0 degrees Celsius above pre-industrial. The 2026 event is developing at approximately 1.4 degrees Celsius above pre-industrial, and against the backdrop of the warmest 12-month stretch in American recorded history, with the warmest 12-month stretch in global recorded history immediately preceding it. The analogies from prior Super El Niños are the best tools available. They are also imperfect tools, applied to conditions that have no historical parallel. Every impact study, every regional forecast, every model projection that draws on the 1997-98 playbook is doing so, knowing that the baseline into which 2026's El Niño is arriving is structurally warmer than the baseline from which the prior event departed. What that difference produces in practice is the question that has no definitive answer yet. What the forecasters can say is what the models converge on. What the models converge on is +3 degrees Celsius by November, and the last time something like that happened, the data wasn't good enough to know it until the famines had already started. There is a specific caveat embedded in the IRE/Columbia May 2026 NSO forecast discussion that, if you read quickly, functions as boilerplate. It is not boilerplate. It reads, "The forecasts are being issued near the end of the boreal spring predictability barrier period. In May, when ENSO forecast uncertainty can still remain elevated. Understanding what the spring predictability barrier actually is, not as a disclaimer, but as a physical phenomenon, is essential to understanding both why the current signals are alarming and why the forecasting community continues to hedge even as the probability numbers climb towards certainty. The spring predictability barrier is one of the most well-documented limitations in all of seasonal climate forecasting. Its core definition is this: ENSO forecast skill drops sharply when predictions are made through the Northern Hemisphere spring, roughly February through May, regardless of how good the models are, how much observational data has been collected, or how confident the forecasters feel. In a perfectly predictable system, a model initialized in March should be able to accurately describe ENSO conditions the following September. In reality, the correlation between model forecasts initialized in spring and observed outcomes drops to roughly 33% or less for the immediately following season, barely better than a coin flip augmented by climatological base rates. The mechanism behind the barrier is rooted in the same seasonal transition that governs everything else about spring. ENSO events typically peak during Northern Hemisphere winter and decay in spring. As the ENSO signal weakens, the signal-to-noise ratio in the Pacific Ocean drops. The anomalies that were clear and measurable in December become smaller and harder to distinguish from background variability in March and April. The ocean-atmosphere coupling that sustains an El Niño or La Niña event weakens during its seasonal transition. In this inherently noisy environment, small errors in the initial conditions, minor uncertainties in where the thermocline sits, in the exact state of the trade winds, in subsurface heat content, propagate rapidly through the forecast. The same model, initialized with slightly different conditions, can produce very different outcomes 6 months later. In practical terms, the spring predictability barrier means that May forecasts for the following winter are historically less reliable than December forecasts for the same winter. The barrier is real and measurable. It has contributed to high-profile forecasting failures, including the 2014 El Niño, that models widely predicted, but that never fully materialized. Here is the critical question. If the spring predictability barrier imposes known limits on ENSO forecasting skill in May, how should we interpret probability numbers like 98% and 100%? The answer is layered and worth holding carefully. The spring predictability barrier is at its most damaging when the ENSO signal is weak or transitioning, when the system is genuinely near neutral and could plausibly go in multiple directions. In those circumstances, forecasts through spring are genuinely unreliable, and the barrier is the dominant source of forecast error. But when the ENSO signal is already strong and consistent, when the weekly Niño 3.4 anomalies are already crossing into positive territory, when multiple independent observational systems are showing the same anomaly in the same direction, the barrier's impact diminishes significantly. The signal-to-noise ratio is high enough that even a noisy forecasting environment can resolve it. The IRI's own analysis notes this explicitly. By March, the barrier is significantly ameliorated, and seasonal forecasters should take advantage of this fact to recover their confidence even as winter ends. By May, the IRI is stating that the Niño 3.4 SSTs have warmed sharply, with the last 3 weekly pentads firmly above +0, 9 degrees Celsius. The weekly data has already surged past the El Niño threshold. The question is no longer whether El Niño will emerge. The question is what peak intensity it will reach. And that is exactly the question the barrier leaves partially open. That distinction is precise and important. The 98% probability from IRI and the 100% from ECMWF are not claims of certainty about peak intensity. They are claims of near certainty about El Niño's presence and persistence. The strength forecast, the 2 in 3 chance of strong or very strong, the 1 in 3 chance of super, carries more residual uncertainty, because that is the part of the question where the spring predictability barrier still has meaningful reach. The forecasting community is not hedging because they doubt El Niño is coming. They are hedging about how strong it will get, because that specific question, asked in May, is exactly where the spring predictability barrier lives. The signals are strong enough to have driven the probability of emergence to near certainty. They are not yet strong enough to have fully resolved the peak intensity. And the gap between those two statements, the certainty of the event and the uncertainty of its ceiling, is where the most consequential meteorological question of the next 18 months currently resides. There is a gap in this story that is worth naming directly, because it is itself the most important thing to understand about where the forecasting community currently stands. The gap is this. The models are saying something the scientists are not quite saying out loud. This is not a contradiction. It is a deliberate, calibrated, professionally appropriate response to a forecasting situation that is moving faster than institutional communication norms are designed to handle. But it is a gap, and understanding it is essential to reading the public statements from NOAA, IRI, and ECMWF correctly. Consider the sequence. In March, the ECMWF assigned 22% probability to a super El Niño. In late April, 80%. In May, 100%. That trajectory from roughly 1 in 5 to certainty in 8 weeks is faster than anything recorded in the lead up to either the 1997, 98, or 2015. 1-6 events. The Kelvin waves subsurface anomaly is running at plus 8 degrees Celsius, warmer than 1997, 98 at the equivalent development stage. 3 independent global modeling systems have converged on a November peak of plus 3 degrees Celsius. Former NOAA chief scientist Ryan Maue posted on May 5th that the updated El Niño forecast was off the charts extreme and explicitly called it code red for the Earth's climate system going into summer 2026. That is the model side of the gap. A former federal chief scientist using language that, in operational meteorology, is reserved for genuinely extraordinary events. Now look at the official language from the institutions themselves. NOAA's May 14th diagnostic discussion states, El Niño is likely to emerge soon, 82% chance in May-July 2026, and continue through Northern Hemisphere winter, 2026. 27, 96% chance in December 2026 February 2027. The CPC's strength forecast describes a super El Niño as the single most likely outcome for late 2026. The IRI's quick look notes that some caution is still warranted as the current forecasts are being issued near the end of the boreal spring predictability barrier period. Both statements are accurate, both are honest, but they are calibrated to different audiences and different risk tolerances. The institutional language is measured, appropriately hedged, and carries within it a 1 in 3 probability of the event not reaching the super threshold, which, translated plainly, means a 2 in 3 probability that even this event, which has generated more model alarm than any El Niño in the modern record, does not reach the peak the media coverage is describing. That is not a small probability to leave on the table. This is the honest framing, and it is worth sitting with. A 1 in 3 chance of a super El Niño is simultaneously a large enough probability to take seriously and a small enough probability to leave the outcome genuinely uncertain. A forecaster who said with confidence that this will be the strongest El Niño since 1877 would be overstating what the science supports. A communicator who dismissed the 1 in 3 odds as negligible would be understating them. The data lives in the space between those two positions, and the hesitation you hear from the scientific community is not timidity. It is precision. What the hesitation is not, however, is a signal that the concern is manufactured. The concern is structural. The 2 in 3 probability outcome, a strong or very strong El Niño that does not clear the super threshold, would still represent an event of substantial global consequence. Northern Hemisphere winters warmer than average across much of the United States. Southern storm track strengthened. Monsoon patterns disrupted. Drought amplified across Australia and parts of sub-Saharan Africa. Global temperature records pushed to new highs. A merely strong El Niño, arriving against the warmest climate baseline in the instrumental record, is not a comfortable outcome. It is the floor of the probability distribution, not the ceiling. What the forecasting community is watching now, the specific data points that will begin to resolve the strength question over the next 8 to 12 weeks, are well defined. Whether the Bjerknes feedback locks in as the Kelvin wave surfaces, whether westerly wind bursts continue across the western Pacific, sustaining the heat supply, whether the weekly Niño 3.4 anomaly crosses convincingly above +1, 0 degrees Celsius in late May or early June, whether the ECMWF and CFS V2 ensemble spreads tighten above +2 degrees Celsius for the autumn window, or begin to show divergence. The answers to those questions will arrive in the forecast discussions. They will be written in the same measured, calibrated language that the Boston office used when it described an approaching heat event as close to the maximum relative to climatology for this time of year. Listen for that language. It is how the forecasting community signals that the data has arrived at a place where the hedging is no longer doing the work it was designed to do. That moment has not fully arrived yet, but the trajectory of the models suggests it is approaching, and the context in which it will arrive, dual heat domes, a European heat wave breaking 100-year records, the hottest 12-month stretch in American history as the baseline, means that when it does, the numbers will land in a system that has no historical parallel. The comparison that climate scientists are now making publicly, the comparison to 1877, requires careful handling. It is not hyperbole. It is not a worst-case framing invented for public consumption. It is the specific historical event that three independent global modeling systems are projecting the 2026 event to match or exceed in peak ocean temperature anomaly. Making that comparison without its full context is irresponsible. Making it without naming it at all would be dishonest. In the summer of 1877, the equatorial Pacific broke from a 6-year cold pattern and released a surge of heat so vast it reorganized the weather of the entire planet simultaneously. What followed was not a regional weather disaster. It was a synchronized global catastrophe. The research that established the 1877-78 event scale and mechanism was published in the Journal of Climate in November 2018, led by climatologist Deepti Singh, then at Columbia University's Lamont Doherty Earth Observatory. The paper's findings are precise and verified. The event is associated with an extraordinary combination of preceding cool tropical Pacific conditions from 1870 to 1,876 inches. 6 years of below-average Central Pacific temperatures, the longest such cold period on record at the time, that drove an immense buildup of warm water in the western tropical Pacific. This is what Singh described with a phrase that is worth quoting for its clarity. It's like a pendulum. If you keep pushing it in one direction further and further from the center, and then release it, it's going to go to the extreme in the other direction. The 1875-76 La Niña was the release. It kicked off dry conditions across India, Mexico, and the southwestern United States, then discharged into the 1877-78 El Niño, one of the two longest duration El Niño events ever observed, persisting for the better part of 2 years. The Pacific warming's drying effect was amplified by two simultaneous secondary ocean anomalies. The Indian Ocean Dipole in 1877 generated the strongest east-west thermal contrast in the Indian Ocean ever recorded before or since, extending drought across Australia, South Africa, and large portions of Africa. And the North Atlantic in 1877 and 1878 ran at its warmest temperatures since records dating back to the 1850s, pushing moisture-carrying atmospheric winds northward and away from Brazil's northeast, which lost 2 million people in the famine that followed. The famine mortality that resulted, quantified regionally by Singh's team, ran to between 12.2 and 29.3 million deaths in India, between 19.5 and 30 million deaths in China, and approximately 2 million in Brazil. Global total exceeding 50 million fatalities. That figure represented roughly 3 to 4% of the estimated world population of 1.3 billion at the time. Translated to today's population of approximately 8 billion, an equivalent proportional toll would be somewhere between 240 and 320 million deaths. Florence Nightingale, writing about the Indian famine in 1877, said, "The more one hears about this famine, the more one feels that such a hideous record of human suffering and destruction the world has never seen before." Singh's team described it in their 2018 paper as arguably the worst environmental disaster to ever befall humanity and one of the worst calamities of any sort in at least the last 150 years, with a loss of life comparable to the world wars and the influenza epidemic of 1919. And three independent global forecasting systems are projecting the 2026 El Niño to match or exceed it in peak ocean temperature anomaly. Now, what must be said carefully alongside that? The 1877 event caused the death toll it did through a convergence of factors that are not fully replicated today. Pre-modern agricultural systems with no buffer capacity. Colonial economic structures that actively redirected food away from famine-affected populations. No international humanitarian response infrastructure. No early warning systems. No satellite observation. The absence of any coordinated food aid or emergency logistics. The deaths of the Great Famine of 1876-78 were a function of the climate catastrophe intersecting with political, economic, and colonial conditions that amplified every human vulnerability to the maximum. The world of 2026 has early warning systems. It has international logistics networks. It has reserve food stocks, though unevenly distributed. These are not trivial differences. But the 2026 event also has something 1877 did not. It arrives in a global atmosphere that is already running approximately 1.4 degrees Celsius above the pre-industrial baseline. The oceans are warmer, the soil moisture baseline is lower, the drought preconditioning across the American West and Southern Europe is already in place. Climate scientist Deepti Singh, now at Washington State University, stated directly in an interview with the Washington Post in May 2026. Simultaneous multi-year droughts similar to those in the 1870s could happen again. The 1877 parallel is not a guaranteed outcome. It is the closest historical analog to what the current Kelvin wave's trajectory is projecting. And the last time the Pacific ran signals like this, the data wasn't good enough to know it until the famines had already started. Today, the data is. The question is what the world does with it. The 1877 event did not emerge from nowhere. It was built. The research establishing its mechanism, published in the Journal of Climate by Deepti Singh's team in 2018, identified a specific structural precondition: 6 years of below-average Central Pacific temperatures from 1870 to 1876, the longest sustained cold period in the observational record. Those 6 years of La Niña-dominated conditions served a precise physical function. They drove the trade winds to strengthen and persist, pushing warm water westward and accumulating it in the Western Pacific, like water behind a dam. By 1876, the warm water volume in the Western Pacific had reached an extreme. When the cold phase finally collapsed into the La Niña of 1875-76 and that discharged into the El Niño of 1877, the stored heat was released in a single catastrophic pulse. The pendulum had been pushed as far as it would go and then released. This is the part of the 1877 story that deserves particular attention in 2026, because the structural setup is not without parallel. From late 2020 through early 23, the Pacific underwent what climate scientists confirmed as a rare triple-dip La Niña, 3 consecutive Northern Hemisphere winters under La Niña conditions, beginning in September 2020 and persisting for approximately 2.5 years. Research published in Nature NPJ Climate and Atmospheric Science in 2025 noted explicitly that the 2023-24 El Niño that followed the triple-dip La Niña emerged after the largest accumulation of warm water in the equatorial Western Pacific since 1980. The recharge oscillator mechanism had been running. The cold phase had been building heat in the west. When the triple-dip finally ended in early 2023 and El Niño emerged, the warm water volume was at a historically elevated level. The 2023-24 El Niño should, by the subsurface heat content logic, have been a major event. Research published in the same journal found that unusual easterly wind anomalies over the tropical western Central Pacific, persisting after the end of the preceding La Niña, significantly slowed that event's development, preventing it from reaching its anticipated intensity. The pendulum swung, but something partially caught it. Then, La Niña developed again in late 2025 and lasted until early 2026, confirmed by the WMO. Not a multi-year event, but a returned cold phase, continuing to maintain the trade wind pattern that suppresses the cold tongue in the east and maintains warm water pressure in the west. When that La Niña collapsed in early 2026, what was the state of the Western Pacific warm pool? The subsurface heat content data, tracked by NOAA's GODAS system and referenced in Severe Weather Europe's analysis, shows a massive subsurface warm pool sitting at depths of 100 to 250 meters across the western and central equatorial Pacific as of early 2026. The pool that is now propagating east as the plus 8 degrees Celsius Kelvin wave currently approaching the surface. The parallel to 1877 is not exact. It is not claimed to be exact. The scientific literature is careful about the limits of historical analogy, and that caution is correct. The 1870-76 cold period was longer, 6 years versus the roughly 3-year triple dip from 2022-23, plus the shorter 2025-26 cold phase. The mechanisms are the same in character, but different in duration and magnitude. The 1877 event also coincided with an exceptionally strong Indian Ocean dipole that amplified its impact across Australia and Africa, a secondary forcing that is not yet confirmed for 2026. What is confirmed is the structural sequence, a sustained cold phase longer than typical. accumulating warm water in the western Pacific through the recharge oscillator mechanism, followed by a rapid phase transition and a Kelvin wave of unusual amplitude. That sequence produced the 1877 event. A version of that same sequence is running now. The 2026 Kelvin wave is running warmer at this development stage than 199798. The models are projecting a peak that would exceed the entire modern record. Where the parallel ends matters as much as where it holds. The 1877 event may have benefited from uniquely extreme conditions in three ocean basins simultaneously: the Pacific, the Indian Ocean, and the North Atlantic, all running at or near record anomalies in the same window. Whether 2026 replicates that full oceanic convergence is genuinely unknown. The Indian Ocean dipole's 2026 behavior is not yet determined. The North Atlantic's role remains an open variable. What the pendulum analogy captures is the mechanism, not the guarantee. The Pacific has been pushed hard in the cold direction for an extended period. The warm water has accumulated. The release has begun. How far the pendulum swings to the other side is the question the next 8 weeks of data will start to answer. In February 2026, the same month the Western Pacific subsurface warming was beginning to accelerate. The same month that above-average sea surface temperatures emerged in the far eastern equatorial Pacific for the first time in the cycle. NOAA's Climate Prediction Center made the first major change to its El Niño classification methodology in 75 years. The old system was called the Oceanic Niño Index, the OONI. It measured the sea surface temperature anomaly in the Niño 3.4 region, the central equatorial Pacific rectangle, as a departure from a rolling 30-year climatological baseline. The problem with that approach in 2026 is precisely the problem that now characterizes every climate metric. The entire tropical ocean is warming. When the baseline you're measuring against is itself rising, the anomaly you calculate, the departure from average, gets smaller. An ocean that is structurally warmer than it was 30 years ago generates a smaller anomaly number even at temperatures that, in absolute terms, are historically extreme. As NOAA put it in its implementation notice, the traditional ONI struggles to keep pace with anomalous changes in tropical sea surface temperature, which is particularly problematic in real time when using a time-lagged climatology. The new system is the Relative Oceanic Niño Index, the RONI. The methodology change is precise. Instead of measuring how warm the Niño 3.4 region is compared to its own historical baseline, RONI measures how warm it is relative to the entire global tropics. The Niño 3.4 anomaly is computed by subtracting the average sea surface temperature anomaly of the global tropics, the belt from 20 degrees N to 20 degrees S, from the Niño 3.4 regional anomaly, then rescaling the result to match the amplitude of the traditional index. The threshold for El Niño classification remains +0, 5 degrees Celsius. But what that threshold is measuring has fundamentally changed. El Niño is now officially defined as the Central Pacific running anomalously warm relative to the rest of the tropics, not anomalously warm in absolute terms. This distinction matters enormously for how the 2026 event will be classified in the historical record, and for how it will compare to prior events. Under RONI, the 2023-24 El Niño, classified as strong under the old ONI, is reclassified as moderate, roughly 0.6 degrees Celsius cooler, in relative terms. The 2020-23 triple dip La Niña is reclassified as one continuous, unbroken La Niña event, rather than three separate phases. A number of events across the historical record have been reclassified, up or down by one strength category. The reanalysis is methodologically sound, but it means that any comparison between the projected 2026 peak and historical super El Niño events requires explicit acknowledgement that the metric has changed. Now, set that aside and look at what the models actually agree on, because the model convergence is the more important story than the index methodology. Three independent global forecasting system, NOAA's Climate Forecast System version 2, the ECMWF's Seasonal Ensemble, and Australia's Bureau of Meteorology have converged on a peak Niño 3.4 anomaly of approximately +3 degrees Celsius in the November 2026 window. That convergence holds under both the old and new methodologies. because it is describing the actual physical state of the ocean, not the classification that falls out of it. The ECMWF projects its peak intensity arriving in November 2026, with above-average conditions extending through the winter of 2026-27. The bomb's trajectory is parallel. The CFSVA-2's median run lands in the same window. 3 modeling centers, different data, different physics. Same peak. That is convergence. What does that convergence mean in operational terms? It means the models have, to a degree unusual for this early stage of development, resolved the event's trajectory. The uncertainty that remains, the width of the model ensemble spread, lies primarily at the high end, in the question of whether November's peak reaches +25 degrees Celsius or +30 degrees Celsius or beyond, not in whether a significant event develops at all. The floor of the probability distribution is a strong El Niño. The ceiling, in the current ensemble, extends toward the level of the 1877 event. The median sits somewhere in between, in territory the modern instrumental record has visited only 3 times. The Roni change means the 2026 event will be measured differently than 1997 and 2015 when the historical comparisons are made. Direct comparison will require methodological translation. That translation is not complex, but it must be done explicitly if the record comparisons are to be meaningful. What it does not change is the physical reality. A Kelvin wave carrying +8 degrees Celsius subsurface anomalies is currently surfacing in the eastern Pacific. 3 independent models project a November peak above any El Niño in living memory, and the global atmosphere is already running at the hottest 12-month baseline in the instrumental record. The index changed. The ocean did not. El Niño does not affect every part of the world in the same way, at the same time, or with the same type of disruption. Its teleconnections are geographically specific, seasonally dependent, and probabilistic rather than deterministic. A strong El Niño shifts the odds. It does not guarantee outcomes. With that stated precisely, here is what the historical record and current climate modeling say about where the 2026-27 event is most likely to leave its mark, region by region. India. India's southwest monsoon, the single most consequential seasonal rainfall event on Earth, supplying 90% of annual precipitation to large portions of the subcontinent and sustaining the agricultural system that feeds 1.4 billion people, weakens during strong El Niño events. The mechanism is direct. The shift in the Walker circulation reduces the pressure gradient that drives moisture from the Arabian Sea and Bay of Bengal inland during the June through September monsoon season. During the 1997-98 event, monsoon rainfall across India ran 14% below normal. Reservoirs dropped 30% according to UN data. Rice, corn, and soybean fields dried up. A 14% rainfall deficit in India is not an abstraction. It is the difference between a normal harvest and a food security event for hundreds of millions of people. The 2026 event is projected to be stronger than 1997-98. Australia and Indonesia. During El Niño, the convective rainfall that normally anchors over the western Pacific, feeding Australia's north and Indonesia's wet season, migrates eastward. The western Pacific cools at the surface. Drought expands across northern and eastern Australia, across Indonesia, Papua New Guinea, and the Philippines. The 2015-16 event produced catastrophic wildfires across Indonesia that generated a smoke blanket covering much of Southeast Asia, contributing to thousands of excess respiratory deaths. The 1982-83 event drove the worst Australian drought of the 20th century at that time. For a region where agricultural calendars and water security are built around the wet season's reliable arrival, its suppression for a full year is not a moderate disruption. It is a structural failure of the regional water cycle. South America. The impact signature splits sharply by geography. Peru and Ecuador. Normally arid. Flood catastrophically during strong El Niño events as warm surface waters pool off the coast and atmospheric convection intensifies. The 1997-98 event produced floods and landslides across coastal Ecuador and Peru that destroyed infrastructure, killed hundreds, and displaced hundreds of thousands. Simultaneously, central Brazil and the Amazon basin dry out as the westward moisture transport that normally sustains the Amazon's wet season weakens. During strong El Niño years, Amazon drought risk increases significantly, a concern that carries both food security and ecosystem implications given the role of the Amazon in global carbon and water cycling. East Africa, the Horn of Africa, Kenya, Somalia, Ethiopia, tends to see above normal rainfall during El Niño events, which sounds positive, but in practice often means flooding, landslides, and vector-borne disease outbreaks. During the 1997-98 event, flooding in Kenya triggered a malaria epidemic that killed more than 1,500 people. The mechanism is not complicated. Too much rain, arriving too fast, in a region without the infrastructure to manage it, creates its own category of humanitarian crisis. Southern Africa moves in the opposite direction. Drought, reduced agricultural output, and elevated food insecurity across a region that in non-El Niño years struggles to maintain adequate grain production. Food security, the aggregated risk. This is the dimension of the global impact map that researchers have spent the most effort trying to quantify, precisely because it is where multiple regional impacts compound into something the international grain trade was not designed to absorb. Studies published in Nature Climate Change and Science have documented the increasing risk of what researchers call multiple breadbasket failure, simultaneous disruptions to grain production in several major agricultural regions at once. El Niño events are the primary driver of this synchronization. Research published in 2025 in Science Direct found that strong El Niño events are projected to cause simultaneous yield losses of between 2 and 8.4% across multiple breadbaskets. For context, in 1982-83, a strong El Niño drove United States maize yields down by nearly 30%, while global yields dropped 11%. Climate scientist Daniel Swain put the core concern precisely in a recent statement. We've never experienced a strong or very strong El Niño event amid pre-existing conditions that were this warm globally. Therefore, it would not be surprising to see some unprecedented global impacts by later in 2026 into 2027 in terms of flood, drought, and wildfire-related extremes. The WMO's current seasonal forecast for the May-June-July 2026 period describes nearly global dominance of above-normal land surface temperatures, with strong regional precipitation variation. That framing, nearly global warmth, highly variable precipitation, is the opening chapter of the El Niño impact sequence. The main chapters arrive in autumn and winter. The United States is not a single country from El Niño's perspective. It is a patchwork of distinct regional climate signatures, each responding differently to the same Pacific Ocean anomaly, often in opposite directions simultaneously. Understanding which direction your region falls in is not just meteorologically interesting. Given the scale of what is being projected for late 2026, it is operationally relevant. The Pacific Northwest is the region with the clearest negative signal. During strong El Niño events, the Pacific jet stream shifts southward, steering the parade of winter storm systems away from Washington and Oregon and toward California and the southern tier. The result is a warmer, drier winter across the Northwest, reduced mountain snowpack, early spring melt, depleted reservoirs, and dry fuels by July. Historical analysis shows that during past strong El Niño winters, the Pacific Northwest averaged 15 to 20% below normal precipitation. Washington state has declared drought emergencies in 4 of the last 5 years, and the snowpack baseline is already compromised from the multi-year cold phase that preceded this event. If the 2026-27 winter runs dry as El Niño predicts, the Pacific Northwest enters summer 2027 with the lowest combined soil moisture and snowpack reserves in its recent history. The wildfire season implications are direct. California is the most consequential wildcard in the domestic picture, and the honest answer is that the historical record provides genuine ambiguity. The 1997-98 Super El Niño delivered record rainfall to California. The 1997-98 winter produced some of the most catastrophic flooding and landslides in the state's history, with damage in the billions. The 2015-16 Super El Niño, which reached comparable ocean temperature anomalies, largely missed California, producing only marginally above normal precipitation. Same classification, radically different outcomes. The current drought.gov analysis notes that El Niño could end 6 years of drought in the southern plains, but cautions that the relationship between ENSO and Southern California precipitation, while statistically positive, has high variance in individual years. A very strong event expands the enhanced precipitation signal northward, which is why California warrants close monitoring if the Pacific continues strengthening toward the +3 degrees Celsius projection. But it is not guaranteed, and anyone who tells you otherwise is overstating what the science supports. The southern tier is where El Niño's domestic signal is most consistent and historically best documented. From California through Arizona, New Mexico, Texas, the Gulf Coast, and across the southeast to Florida, El Niño strengthens and pushes southward the subtropical jet stream, the atmospheric highway that guides winter storm systems across the southern United States. The result is wetter and cooler winters across this entire corridor. NOAA data shows El Niño winters typically deliver 2 to 5 inches above normal precipitation from Texas to Florida. The southern plains and Gulf Coast have the most to gain in hydrological terms. 6 consecutive years of drought in parts of Texas and Oklahoma could finally see meaningful recharge. The flip side is elevated flood risk, particularly in already saturated soils after heavy rainfall, and an increased risk of severe weather outbreaks along the active southern storm track. The northern tier, the upper Midwest, Great Lakes, New England, and Western Canada, runs warm and dry during El Niño winters, as the storm track is pushed south and the cold air that normally penetrates from Canada is deflected. The Midwest typically averages 3 to 6 degrees Fahrenheit warmer than normal through the winter. Snowfall decreases across the Great Lakes and northern plains. Energy demand for heating typically drops. This is the one unambiguously positive signature for a large portion of the country. Though even here, the warmth that suppresses winter heating bills also reduces snowpack in the northern headwaters of river systems that feed agriculture through the spring and summer. Two things must be said clearly about all of these regional projections. First, El Niño shifts the odds. It does not guarantee outcomes. The 2015-16 event demonstrated that the Southern California wet signal, one of the most statistically robust El Niño teleconnections in the Western Hemisphere, can fail in an individual year. Cold outbreaks can still penetrate the north. The southern storm track can produce catastrophic flooding rather than beneficial drought relief. The signal is real and operationally useful. Individual event outcomes within that signal envelope remain uncertain. Second, this event, if it develops as projected, will arrive against the warmest background climate state the United States has ever experienced during an El Niño. Every precipitation event will carry more water vapor than historical analogs suggest, because a warmer atmosphere holds more moisture. Every flood will have a warmer baseline from which it departs. Every drought will bake into soils that are already depleted. The historical playbook is the best available guide. It is not a perfect guide for a climate that has no historical parallel. On May 22, 2026, NOAA released its official outlook for the Atlantic hurricane season. The forecast called for 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes reaching Category 3 or above. NOAA placed a 55% probability on the season finishing below normal. Colorado State University, which pioneered seasonal hurricane forecasts in 1984, issued a parallel forecast of 13 named storms and 6 hurricanes, the fewest storms CSU has predicted since 2019. For context, an average Atlantic season, based on 1991 to 2020 climatology, produces 14 named storms, 7 hurricanes. The 2026 season is projected to land near or below those averages across every metric. This is the inversion at the center of the 2026 story, and it is worth holding clearly. The same Pacific Ocean warming that is loading the global atmosphere toward its most consequential climate event in a century is simultaneously projected to deliver one of the quieter Atlantic hurricane seasons in recent memory. The same El Niño, opposite effects, different hemispheres, different basins, different mechanisms. The mechanism behind Atlantic hurricane suppression during El Niño is well established. When the tropical Pacific warms anomalously, the heating drives enhanced convection and strengthened upper-level winds over the tropical Atlantic and Caribbean, a phenomenon called increased vertical wind shear. Wind shear is the atmospheric hurricane killer. It describes the change in wind speed and direction with altitude, and when it is strong, it physically tears developing tropical systems apart before they can organize into hurricanes. A tropical disturbance trying to strengthen in a high shear environment is like trying to build a house in a wind tunnel. The stronger the El Niño, the more aggressive the wind shear over the Atlantic Main Development Region. NOAA's National Weather Service Director Ken Graham summarized the competing forces directly in the agency's forecast briefing. Atlantic sea surface temperatures are above normal, a factor that in isolation would favor an active season. But El Niño's wind shear is expected to win the tug-of-war. Historically, El Niño years average approximately 10 named storms and 5 hurricanes in the Atlantic, compared to La Niña years, which average closer to 14 named storms and 7 hurricanes. The 2015-16 Super El Niño produced only 11 named storms. The suppression signal is the most robust and consistent teleconnection El Niño has on North American weather. But the honest accounting requires 2 caveats that NOAA's own director stated explicitly. First, a below-normal season forecast is not a safe season forecast. Hurricane Andrew formed during the 1991-92 El Niño and caused $27 billion in damage. The 2004 El Niño season produced 4 hurricane landfalls in Florida. The 1992 season had only 6 named storms total, and one of them was Andrew. A quiet Atlantic season with a single major hurricane making landfall on a densely populated coast produces exactly as much devastation as an active season, with the same landfall. Seasonal forecast suppression is a statistical statement about basin-wide activity. It is not a statement about any individual storm. Second, the warm Atlantic sea surface temperatures that are currently above normal represent a competing forcing that creates genuine uncertainty in the forecast. NOAA's accumulated cyclone energy projection runs 45 to 115% of median, an unusually wide range that reflects the tension between El Niño's suppressive wind shear and the Atlantic's anomalous warmth. The fact that CSU's forecast is the most conservative since 2019 reflects high confidence in El Niño's suppression. The fact that NOAA's upper range still allows for a near-normal season reflects intellectual honesty about that competing factor. The inversion is real and it is consequential. The event that is building in the Pacific, an event with the potential to become the most powerful El Niño in the modern record, will, by the same mechanism that makes it devastating for global agriculture, drought, and heat, simultaneously reduce the threat of major Atlantic hurricane landfalls during the peak summer and early fall window. One ocean warming event. In the Atlantic, a shield. In the global system, a driver of cascading disruption across every continent it touches. Same signal, radically different downstream consequences depending on where you're standing. Every El Niño adds heat to the global atmosphere. This is not a secondary effect or a byproduct. It is the primary mechanism by which the event makes itself felt at the planetary scale. When warm water that has been stored in the subsurface ocean rises to the surface and spreads across the equatorial Pacific, the ocean releases enormous quantities of heat directly into the overlying atmosphere. That release compresses into roughly 12 to 18 months, and its effect on global average temperature is measurable, consistent, and well documented across the historical record. A typical El Niño adds between 0.1 and 0.2 degrees Celsius to the global average surface temperature during its peak. That number sounds small. It is not small. The difference between the warmest year in the modern record and a normal year runs in that range. A 0.1 to 0.2 degrees Celsius pulse, applied on top of an already anomalously warm baseline, is the difference between a historically warm year and a record-shattering one. The critical timing detail is the lag. El Niño's warming effect on global average temperature does not peak at the same time as the ocean temperature anomaly peaks. There is typically a delay of several months, roughly 6 to 12 months, between the peak of the Niño 3.4 sea surface temperature anomaly and the peak of the global atmospheric temperature response. The ECMWF is projecting the current event's ocean temperature peak in November 2026. That lag pushes the maximum global temperature impact into 2027. James Hansen and his colleagues at Columbia University's Earth Institute published their global temperature projection for 2025, 2026, and 2027 in December 2025. Their projection for 2027 is +1, 7 degrees Celsius above the 1880 to 1920 pre-industrial baseline, a figure that would represent a new record for global average temperature. and would exceed the Paris Agreement's 1.5 degrees Celsius guardrail by a substantial margin. The projection assumes a strong El Niño developing in late 2026, consistent with current model projections. Hansen's team noted explicitly that this would provide further confirmation of the recent global warming acceleration. They are not hedging. Carbon Brief's parallel analysis, published in April 2026 and drawing on 5 separate temperature datasets, NASA, NOAA, the Met Office Hadley Center, Berkeley Earth, and Copernicus/ECMWF, projects 2026 itself as the second warmest year on record, with a best estimate of 1.47 degrees Celsius above pre-industrial levels. Their analysis assigns a 62% probability to 2026, finishing between the 2023 and 2024 records. A 19% probability of 2026 setting a new all-time record outright, and a roughly 30% chance of 2026 becoming the second consecutive year to exceed 1.5 degrees Celsius above pre-industrial. The record-breaking year in Carbon Brief's framework is more likely to be 2027, when El Niño's lagged temperature pulse arrives in full. What makes Hansen's projection more aggressive than Carbon Brief's is a methodological difference in how they account for the underlying warming trend. Hansen's team argues that ocean baseline temperatures are running structurally warmer than the preceding El Niño year by approximately 0.13 degrees Celsius, independent of the ENSO signal. That additional structural warmth, compounded with the El Niño pulse, is what drives his projection toward record-breaking territory for 2026 itself, and his 1.7 degrees Celsius figure for 2027. Whether Hansen or Carbon Brief is closer to the verification will be known by this time next year. Both projections describe a global temperature trajectory with no historical parallel in the instrumental record. The wider significance of these temperature projections runs beyond their record status. The Paris Agreement's 1.5 degrees Celsius target was never conceived as a ceiling that could be briefly exceeded in a single El Niño year, and then called a failure. It was conceived as a long-term average, a threshold of persistent warming above which climate risk escalates across a defined set of physical and biological tipping points. A single-year exceedance, followed by a return toward lower values when the El Niño dissipates, is not a Paris failure in the technical sense. But it is something. It is a preview. It is the atmosphere showing us what a warmer future looks like, at full resolution, before it permanently arrives. Every day of 2027 at +7 degrees Celsius, every heatwave, every monsoon disruption, every bleached coral system, every drought-stressed breadbasket is a direct experience demonstration of the world the long-term trajectory is heading toward. Not an anomaly, a preview. The El Niño that is building in the Pacific right now is going to push the global temperature record to a new high. That is not a speculation. It is the consensus projection of every major climate modeling center on Earth. The only questions are how high and for how long before it comes back down. And both of those questions are determined by the same Kelvin wave that is, at this moment, surfacing in the eastern equatorial Pacific and beginning to announce itself at the sea surface. There is a dimension of the 2026 situation that receives almost no coverage in the mainstream forecasting discussion, and it is arguably the most consequential gap between what the models say and what the observations are showing. It is not about El Niño's peak intensity. It is about what happens to concurrent extremes, the simultaneous occurrence of multiple hazards across different regions, when a strong El Niño event arrives in the warmest climate system in recorded history. The gap is this. The climate models that generate the forecasts and impact projections being discussed in every newsroom right now systematically underestimate the risk of synchronized climate extremes. This is not speculation. It is a finding documented in peer-reviewed literature. A 2023 study published in Nature Communications, led by Kai Kornhuber and colleagues, examined the ability of state-of-the-art climate and crop models to reproduce high-impact events involving a strongly meandering jet stream, precisely the atmospheric configuration discussed in this video. The finding was direct. While climate models accurately simulate the large-scale atmospheric patterns, the associated surface weather anomalies and their negative effects on crop responses are mostly underestimated in bias-adjusted simulations. The models get the circulation right. They get the magnitude of the surface impacts wrong. Systematically, on the low side. A parallel study published in Science Advances found that concurrent climate extremes, the simultaneous occurrence of temperature and precipitation extremes across multiple regions, are more frequent in observations than models project. Research published in 2025 in Geophysical Research Letters documented that synchrony of extreme heat and precipitation events has increased worldwide since 1979, especially in the tropics and northern high latitudes, and projects further amplification under warming. What this means operationally is that the impact projections attached to the 2026 El Niño forecasts, the regional drought and flood predictions, the crop yield disruption estimates, the food security assessments, are built on models that have a known tendency to understate the degree to which multiple breadbasket regions fail simultaneously. The risk estimates are the best available. They are also, by the evidence of the observational record versus the model output, likely conservative. There is a second modeling gap that is less frequently acknowledged. The RONI change implemented in February 2026, discussed in Part 15, resolved one source of measurement drift by re-anchoring ENSO classification to a relative rather than absolute baseline. But it introduced a new comparison problem. Every historical impact study, every analog year, every regional forecast built on the 199798 or 2015-16 playbooks was calibrated against the old ONI. Under ORONI, the 2023-24 El Niño is reclassified as moderate rather than strong. That reclassification changes the denominator against which the 2026 event is being compared. When forecasters say the 2026 event is projected to exceed 199798, they are making that comparison across a methodological divide that did not exist when those historical analogs were studied. The CPC is explicit about this. RONI is designed so that a 1950 event and a 2025 event are compared equally regardless of changing ocean temperatures. That is scientifically sound, but the impact literature, the agricultural vulnerability studies, the humanitarian response planning documents, all of them were built using ONI. The translation is not impossible, but it requires explicit acknowledgement that is largely absent from the public discussion. The honest accounting of what the models are missing is not an argument for alarm beyond what the data supports. It is a methodological caution. The numbers that forecasters are publishing, the probability figures, the impact projections, the crop yield estimates are grounded in models with documented low biases for concurrent extremes, calibrated against historical analogs that used a now superseded measurement system being applied to a climate baseline with no direct historical parallel. The models are the best tools available. The observations are telling us they are not the ceiling. What the atmosphere is becoming is something the models are still in the process of learning to describe. The gap between model and observation is narrowing. It has not closed. And the year in which that gap matters most is the year when the largest El Niño in the modern record is converging with the warmest background climate state in the instrumental record. The cold front will arrive, the pattern will reset, the atmosphere will go back to looking quiet for a time. That is always how it works. The heat domes that are baking both coasts right now will break. The European heat wave that set back-to-back all-time May records at Kew Gardens will moderate. The severe weather outbreak that put tornado warnings in Nebraska and fire weather watches in Wyoming simultaneously will run its course. By the end of this week, the operational forecasters will be writing about a return towards seasonable temperatures. The national weather map will look manageable again, and then the next configuration will form. That is the open loop this video has been building toward, not the current heat domes, though they are historically significant and directly consequential right now for the 67 million Americans whose grid operator declared an energy emergency in mid-May, for the 57 Philadelphia schools that closed because their buildings couldn't handle the heat, for the 5 people who died from heat exposure in the United Kingdom in late May, not the tornado outbreak or the fire weather corridors or the European records. Those are the symptoms of the current pattern. The open loop is the pattern itself. What produces it? What is amplifying it, and what is building in the Pacific that will redefine the context in which every subsequent pattern operates? Here is what the data says, plainly. The United States just closed the warmest 12-month stretch in 132 years of climate records, the driest January through March in recorded history. nearly 60% of the country under drought. The March 2026 heat dome was the most anomalous month in the entire national climate record. Not the hottest summer month, not the hottest July. The most anomalous month across all 12 calendar months in 132 years of data. The 2021 Pacific Northwest heat dome, which researchers described as the hottest the region had been in a millennium, was a 1 in 10,000 year event. The March 2026 event was described by the World Weather Attribution Team as virtually impossible without human-induced climate change. Europe's all-time May temperature record was broken twice in 2 days this week, at a station with records going back to 1922. And El Niño hasn't started yet. Beneath the eastern equatorial Pacific, the Kelvin wave is surfacing. 3 independent modeling systems have converged on a November peak of +3 degrees Celsius. The ECMWF is at 100% probability for a super El Niño. IRI Colombia is at 98%. NOAA's CPC calls it the single most likely outcome. The spring predictability barrier is waning. The signal is resolving. The answer is arriving in the data at roughly the rate a forecaster would expect. One model update at a time, the ensemble spread tightening, the probability numbers climbing toward the ceiling. What will the atmosphere look like when El Niño fully arrives? The honest answer is, we know the shape of the answer, and we don't know the magnitude. The shape is documented. El Niño will shift the Pacific jet stream southward. It will strengthen the southern storm track across the United States. It will suppress the Atlantic hurricane season. It will weaken India's monsoon. It will dry out Australia and Indonesia. It will flood coastal Peru and Ecuador. It will push 2027 toward the warmest year in the instrumental record. It will compound a drought preconditioning already built into the soil of most of the western United States after the driest start of year in recorded history. These are the shapes. They come from 75 years of ENSO observations, from the 1997-98 playbook, from the 2015-16 playbook, from the 1982-83 playbook, but climate scientist Nathan Lenson said it directly. Climate change has made El Niño events of the past less informative for events today. The playbook was written for a cooler world. Every precipitation event in a warmer atmosphere carries more water vapor. Every heat wave departs from a higher baseline. Every drought bakes into soils preconditioned by the driest start of year in recorded history. The analogs are the best available guide. They are guides to a terrain that has subtly changed since they were drawn. The specific data points the forecasting community will be watching over the next 8 weeks are well defined. Whether the weekly Niño 3.4 anomaly crosses convincingly above +1, 0 degrees Celsius in late May or early June, it was at +0.9 degrees Celsius in the last reading. Whether westerly wind bursts continue to fire across the western equatorial Pacific, sustaining the heat supply from the warm pool. Whether the ECMWF and CFSV2 ensemble spreads tighten or diverge for the August through October window. Whether the Bjerknes feedback locks in as the Kelvin wave surfaces, beginning the self-reinforcing amplification that characterized every prior Super El Niño development. Those signals will arrive in the forecast discussions. They will be written in the same measured, calibrated, careful language that the Boston National Weather Service office used when it described May's heat event as close to the maximum relative to climatology for this time of year. When you hear that kind of language again, and you will hear it again before this year is out, you will know what it means. Not alarm. Precision. The operational language of people who are watching something they have never seen at exactly this configuration of intensities, choosing their words with the care that the situation requires. The wave that produced today's pattern, the dual heat domes, the European records, the grid emergency in Philadelphia, the tornado warnings in Nebraska, will break in the days ahead. What comes after it is already in the data. The summer pattern is loading, and the Kelvin wave is surfacing, and the models are converging, and the question the forecasters cannot yet fully answer is how many more days like today the rest of this year is going to contain. The answer, when it arrives, will arrive the same way today's pattern arrived. Quietly, on a forecast model discussion 5 days in advance, in language the operational offices will use as carefully as Boston used theirs in May. Anomalous, record-threatening, close to the maximum relative to climatology for this time of year. Listen for it. because the next wave is already in the data, and the one after that is building in the Pacific. This is not the end of the pattern. This is the beginning of what the atmosphere is allowed to do.